So, good evening. Sorry for being late. So, today we will do chemical properties of phenol. Okay, so Sahil, Ashish, Praharsh, Charitre, Vasant, Harshil, Swati, Harsh, Yash, Sad, Rishi. Okay. So let us start. Okay. So chemical properties of phenol. ठीक है? Okay. Okay, good evening. Today, Samir, I will take care of you all. So, chemical properties, first of all, phenol. Phenol has OH group. So, when phenol is treated with zinc dust, then we get benzene. Means zinc dust act as reducing agent. Very important reaction. To convert phenol into benzene, we use zinc dust. Done. Means it is visible to you. So, when we treat phenol with zinc dust and we slightly heat it, we get benzene along with zinc oxide. Okay, so this is the reaction of phenol with zinc dust. Metals are strong reducing agents. Okay, and here zinc is used because reaction is gentle with zinc dust. Okay, second is when phenol we treat it with sodium dichromate, when we treat it with sodium dichromate or potassium dichromate even and H2SO4, it is converted into quinone, or we can write it as benzoquinone. Phenol, because dichromate, sodium or potassium dichromate, they are strong oxidizing agent in acidic medium. So phenol is converted into benzoquinone. Even we can convert phenol into aniline under vigorous conditions. Okay, under vigorous conditions, phenol can be converted into benzene. How can we do it? We just treat it with ammonia in the presence of anhydrous zinc chloride at 573 Kelvin. So we get ammonia along with H2O. This anhydrous zinc chloride act as dehydrating agent. It acts as dehydrating agent in this reaction. So say we can convert phenol into benzoquinone, we can convert phenol into benzene, or we can convert phenol into aniline. It should be NH2 into aniline by using these reagents. Okay, even if we treat phenol, okay, we can write here, if we treat phenol with acid chloride in the presence of pyridine, or phenol with acetic anhydride phenol with acid chloride, this is esterification. What is the product formed? Just tell me. Tell me fast. If we treat phenol with acid chloride just like alcohol with acid chloride, or acid anhydride, so it should be 1O, because acid anhydride is formed when we have two acids in the presence of concentrated H2SO4. So water is removed and we get this is acetic anhydride, ethanoic anhydride, right? So it is taking place in the presence of concentrated H2SO4 or even sodium acetate. So what is the product formed? Chlorobenzene. When we have alcohol, it should be ester. Formation of ester takes place. H and Cl is removed. HCl is removed, and we get OCOCH3. This whole COCH3 attached to O. Esterification takes place. Am I right? So it is actually phenyl acetate along with HCl, and this HCl is neutralized by pyridine, because pyridine is a base. What is pyridine? It is like this. Okay, this is pyridine. So pyridine is a weak base which is used to neutralize HCl. Okay, in this case again H and this whole thing CH3COO give acetic acid along with again same product phenyl acetate along with acetic acid. Phenyl acetate along with acetic acid. Okay, this is just esterification. Here in last we have done esterification like this, if you remember. This HCl is removed and we get ROCOCH3. Right? Same is the case here. Okay? Now this is called acylation. This is actually, these are called product of acylation. Okay, and we get phenyl acetate. And this phenyl acetate when it is treated with anhydrous AlCl3, then another reaction takes place, okay, on heating, and we get OH COCH3 plus OH COCH3 means para-hydroxyacetophenone or ortho-hydroxy acetophenone. Para-hydroxyacetophenone and ortho-hydroxy acetophenone. So in this way, this reaction is called Fry's rearrangement. Not in the syllabus, but questions are asked in competitive exams. Okay, so this phenyl acetate, when it is treated with or when it is heated with anhydrous AlCl3, we get ortho-hydroxyacetophenone or para-hydroxyacetophenone. Okay, next is benzoylation. Just like acylation, there is benzoylation. In this case, phenol is treated with benzoyl chloride. In the presence of NaOH. So tell me, what is the product formed in this case? Just like acylation, H and Cl are removed and we get OCO C6H5. Okay, this reaction is called Scotton Bowman reaction. Scotton Bowman reaction, and it is actually phenyl benzoate. तो हेलो बेटा, जरा जोर से मत बोलो, मेरी क्लास चल रही है. दर्श, चिल्लाओ मत. ये मकान मेरा है फर्स्ट फ्लोर पे. देखो, हाँ, वेरी गुड बेटा, वेरी गुड. COC6H5. So phenyl benzoate is formed, and this particular reaction is known as Scotton Bowman reaction, benzoylation reaction. Okay, it is again esterification. Ester is formed. alcohol when react with Grignard reagent. Let us take case of methyl magnesium bromide. So tell me, what is the product found in dry ether? Because methyl magnesium bromide or any Grignard reagent is reacting in anhydrous condition. Yes, tell me, what is the product form? Yes, it is your turn. Fast. Okay, HBr. Wrong. Yes, anyone else? Very good. MgBr OCH3. MgOCH3. Wrong, Sahil. Fast. Respond fast. Yeah. Say, in this case, phenol gives phenoxide ion and H plus ion. This one will give CH3 negative and MgBr positive. So CH3 negative attached to H plus. So we get methane. One of the hydrocarbon is formed just like in alcohol. Okay, and along with this. Okay, these are the products formed. Phenoxy magnesium bromide. Okay, phenoxy magnesium bromide. Okay, along with hydrocarbon, along with methane. Okay, this is the product formed. Done. Now reaction with neutral ferric chloride. Reaction with neutral ferric chloride, neutral FeCl3. So phenol, phenol can be written as C6H5OH. When it is treated with FeCl3, the product formed is C6H5O, 6 hexa coordinated complex is formed, and it gives violet coloration. It has violet coloration. Okay, in the presence of FeCl3, it gives violet coloration. Very important reaction. It is used as a test for phenol, that when phenol is treated with neutral ferric chloride, it gives violet coloration. And even not phenol, all organic compounds having enolic group. Enolic group means double bond COH. Any organic compound having this enolic group can give test or can react with neutral FeCl3. And you know, phenol is enolic. Phenol is enolic. You know, phenol, there is double bond, C double bond C and OH. Double bond C and OH. So it is also enolic. Phenol is also enolic. So any organic compound having enolic group can give test with neutral ferric chloride. Not violet only. There are various colors, different colors, violet to blue, green, or even red, right? But with phenol, it gives violet coloration. So it is a test for phenol. Keep in mind. Okay. With acetic acid, even it react carboxylic acid, but give buff colored precipitates. Okay. Yes. So we get with phenol, with Grignard reagent it gives methane or any hydrocarbon, okay, RH, and with neutral ferric chloride it gives hexa coordinated complex of iron and which is of violet color. Okay. Now electrophilic substitution reactions of phenols. Can I write? No. Of phenols. So you know, now tell me, out of phenol and benzene, which one is more reactive towards electrophilic substitution reactions? Yes, it is your turn now. Out of phenol and benzene, which one is more reactive? Respond fast. Sahil, you are, I don't want to say anything. What about others? You are right or wrong, I'll let you know. Where is methanol, Ashish? Out of phenol and benzene, which one is more reactive towards electrophilic substitution reaction? That is the question. Out of phenol and benzene, which one is more reactive towards electrophilic substitution reaction? Wrong. Benzene is not the right answer. Sahil is right, because that's why I used sarcastic language, so that you will answer like that only. Say, you know, phenol, in phenol OH group has plus R and minus I effect, and you know, plus R is dominating over minus I effect. So overall OH group is electron releasing group. So it increases electron density on benzene ring as it increases electron density, electrophile can easily attack. Electrophile can easily attack on the ring. So OH is activating group. OH activate the ring towards electrophilic substitution reaction, right? And as it increases electron density, particularly at ortho and para position, it is ortho-para directing. Means OH group is activating and ortho-para directing. OH group is activating and ortho-para directing. So phenol is more reactive than benzene towards electrophilic substitution reactions. Got my point? If you have any doubt, please do ask. Okay, Saad, it's okay, but let me know. You people got the answer right, or got it? This explanation? Got this explanation? Okay, great. Now, so whenever there is an electrophilic substitution reaction, when OH is attached, most of the time only ortho and para products are formed. Ortho and para products are formed because OH group is activating as well as ortho para directing. Okay, now let us do first substitution reaction, that is halogenation. So in case of halogenation, in most of the cases when chlorination takes place, we use anhydrous AlCl3 or FeCl3, means one of the Lewis acid is used along with halogen. Same bromine along with Lewis acid we are using like this only. But keep in mind, when halogenation of phenol takes place, as OH is activating group, because of its activating nature, we can do chlorination or bromination in the absence of Lewis acid, because OH can activate the ring to such an extent and it polarizes the halogen as well. So if it takes place in the presence of water, means in aqueous medium, then we cannot stop the bromination up to mono stage, monohalogenation. There is formation of 2,4,6 tribromophenol. There is a formation of 2,4,6 tribromophenol. and it has white PPT. Right? But to stop it up to mono halogenation stage, for that what we do, we use phenol in non-polar medium like CCl4, CS2, okay? Non-polar medium, polar medium. In polar medium we get tribromo product, and in case of non-polar medium we get 2-bromophenol and 4-bromophenol. Means mono halogenated products are formed. 2-bromophenol, 4-bromophenol. Okay? Now why is it so? So say, phenol and phenoxide ion. So tell me, out of phenol and phenoxide ion, which one is more polar? Okay, is it like that? Very good. Sahil, phenol is more polar, phenoxide ion is more polar than phenol because it has partial positive, partial negative, partial positive charge. It has complete negative charge. So phenoxide is more polar. And like dissolves like. Like dissolves like. And at the same time, phenoxide ion is more resonance stabilized than phenol. Or O negative is more electron releasing, stronger electron releasing group than OH itself. Both are electron releasing group, but this is less electron releasing group and this is more electron releasing group. And this is more polar. This one is less polar. So less polar solvent favors this phenol and more polar solvent favors phenoxide ion. So when we use water, phenol is in the form of phenoxide, which is more activating group, which is stronger activating group, more electron releasing, and that's why we get tribromophenol. Okay, we cannot stop it up to mono-bromo stage. But in case of bromination in non-polar medium, this exists as phenol only, which is less electron releasing group, and we get mono-bromo products. Yes, any doubt? Beta, CS2 is a non-polar solvent because we need medium. Non-polar solvent, even we can use carbon tetrachloride, which is also non-polar medium. Okay, so in non-polar medium, phenol exists as such, which is less electron releasing, but in polar medium, phenol exists as phenoxide ion, which is more electron releasing group. Okay, and more activating, so we get tribromo product. Sahil? Did you understand? Sahil? Okay, done. So this is about halogenation. Now next is halogenation, let us do sulfonation. So tell me the reagents used for sulfonation. Yes. Sahil, sulfonation. For sulfonation, what we use? We use either we use oleum or concentrated H2SO4. So sulfonation in the presence of concentrated H2SO4 at 283 to 293 Kelvin. Say at low temperature, very good beta, concentrated H2SO4. Okay, so if we use low temperature, then we get orthohydroxybenzene sulfonic acid, or we can say 2-hydroxy, yet simply 2-phenol sulfonic acid. We can write it like this, or we can write 2-hydroxybenzene sulfonic acid. Okay, then at low temperature this is the major product, but if temperature is high, means at 373 Kelvin, sulfonation with concentrated H2SO4 at high temperature, then we get 4-phenol sulfonic acid. So 4-phenol sulfonic acid is the major product when temperature is 373 Kelvin and along with water, and 4-phenol sulfonic acid is the major product when temperature is 373, or even 2-phenol sulfonic acid can be converted into 4 when we heat this. So this is actually kinetically controlled product. This is kinetically controlled product. And this one is thermodynamically controlled product. Can we write here? Yes. This is thermodynamically controlled product. Yes, para product is formed at 373 Kelvin, ortho product is formed at low temperature. So keep in mind, any product which is formed at low temperature is kinetically controlled product, and any product which is formed at high temperature is thermodynamically controlled product. That means this product is more stable because at high temperature it survives. At low temperature it can survive. Okay? So this is about sulfonation. Now let us do nitration. Yes, tell me, what are the products, what are the reagents used for nitration? Or we can say nitrating mixture. What is nitrating mixture? Nitration. Okay, very good. It is Asar, Savan, very good. It is nitric acid and sulfuric acid. Means nitration takes place in the presence of concentrated HNO3 and concentrated H2SO4. Okay, so this nitrating mixture, when it is used, and you know phenol is highly activating group, and we use nitrating mixture or even you know HNO3 concentrated is also an oxidizing agent. It is an oxidizing agent, right? So if we use concentrated HNO3, then we get 2,4,6 trinitrophenol. But yield is poor. Its yield is poor. 2,4,6 trinitrophenol, that is also called 2,4,6 trinitrophenol, which is also called picric acid. Okay, but its yield is poor, right? As its yield is poor, to increase its yield, what we do? First we sulfonate it. First we sulfonate the phenol, and when we sulfonate at 373 Kelvin, you know, we get main product formed is para along with ortho to small extent. Major product formed is para at 373, but along with small amount of phenol. And when these products are undergoing nitration, then nitration plus desulfonation takes place simultaneously, and yield is improved. Yield is increased. Right? Got my point? Okay, very good. So phenol can be converted to picric acid directly, but yield is very poor. Why is it so? Because as phenol is highly activating group, HNO3 is an oxidizing agent, so most of the phenol is oxidized. Most of the phenol is oxidized before nitration. Right? So better to go by this route. First we sulfonate it, because when we sulfonate, this SO3H group is withdrawing group, and that's why its activity is somewhat decreased, and then we do nitration. So we get the same product, but now with better yield, because now nitration takes place with desulfonation. Okay? Right. Now if phenol is titrated with dilute HNO3, then we get orthonitrophenol and paranitrophenol. We get orthonitrophenol as well as paranitrophenol. So 2-nitrophenol and 4 nitrophenol. Even dilute HNO3 can oxidize phenol, and product formed are 40% 2-nitrophenol and 13% 4-nitrophenol. But these can be easily separated by steam distillation. How is it possible? Because orthonitrophenol in this case there is intramolecular H bond. There is intramolecular hydrogen bonding, and due to this intramolecular hydrogen bonding, it has low melting point, low boiling point, its solubility is low solubility, and it is weaker acidity. Weaker acid, because this H is involved in intramolecular hydrogen bonding, therefore it is difficult to remove it. So its melting point becomes low because it is stable in its own thing, and this is called chelation. 1, 2, 3, 4, 5, 6. 5 or 6 membered ring is formed by intramolecular hydrogen bonding, that is called chelation. Okay, and because of this chelation, it is not associated with the other nitrophenol. It is stable in its own. That's why it becomes slightly inert. Okay, and that's why its melting point becomes low, its boiling point becomes low, its solubility decreases, and it is a weaker acid, and it becomes steam volatile. It is steam volatile. Okay, but paranitrophenol, in paranitrophenol, there is intermolecular H bonding, and due to intermolecular H bonding, boiling point is high. Even solubility is more, everything is high now. Okay, so it becomes steam non-volatile. So orthonitrophenol can be separated from paranitrophenol by steam distillation. Orthonitrophenol go with the steam, okay, and paranitrophenol remains in the mixture. Okay, in this way we can separate orthonitrophenol from paranitrophenol. Okay, now to prepare single product, that is only paranitrophenol, because that is better choice, because here we get mixture. So to get only para product, what we do, first we treat phenol with nitrous acid, mixture of NaNO2 and HCl. By using this mixture we get HNO2. Okay, so at around about 280 Kelvin, so we get treated with dilute HNO3, it undergoes oxidation and we get the desired product, that is para-nitrophenol. See, phenol, first it is converted into para-nitrosophenol. This is para-nitrosophenol, and finally we get para-nitrophenol as a single product. There is no orthonitrophenol because OH group is ortho-para directing, so obviously otherwise we get two products. But when we use nitrous acid, we get para-nitrosophenol as the sole product, and on oxidation with dilute HNO3, we get para-nitrophenol as the only product. Okay? Very good, Sahil. Sahil, very good, beta. Now, Fiddlecraft alkylation. Oh, so that's all for the day. See you tomorrow at the same time. Bye bye. Samir, is it okay? Okay, Jai Janendra. Okay, bye bye. Bye, beta, bye. Okay, Vasant, I take care, but you too. Bye, Harshil. Okay, Ashish, Jai Janendra. Okay, bye.